Oh good, that was the one mistake for the talk out of the way. So if you've run into me in the days before this presentation and seen my badge, or if you've seen the quote on the Silly Silliness post on the LCA blog, you might have seen this particular line, I ported Python to GRUB. And invariably the reaction to this is a big flat, what? And this tells me that I was entirely successful in that description. It certainly seems to draw attention. So I want to give an overview of exactly why I'm doing this, trying to get BIOSes tested, firmware tested, understand what's going wrong with it, and explain what can go wrong with that, why is it that we want to test them in the first place, a brief history of the project that I'm working on this with that involves porting Python to GRUB, a tour of what it can do, a little demo of some of that functionality, and some info on how to write tests so that you can make your BIOS of choice just a little bit less buggy. So to start off with, the BIOS on your system, usually think of the BIOS as being the bare minimum functionality you need to get out of the way and boot an OS. And usually you want it to hurry up and get out of the way. And there's this general perception that Linux doesn't really need the BIOS. So it just ignores the BIOS anyway. Once you've booted it, it'll go do its own thing and try to not touch the BIOS at all. But it turns out there's a couple of things that we still care about deeply that the BIOS does. We care about platform configuration, however it's been programmed, however all the chipset registers, CPU registers, and so on have been programmed. And we care about these various interfaces to platform functionality that still matter after boot time. So platform configuration is all about taking this highly configurable hardware that doesn't want to have to be re-etched out of silicon every time it needs to be changed, taking it from the bare minimum configuration that's known to work that we boot up in, and putting it into some kind of optimal configuration that we'd prefer to be using. And that involves programming the CPU and chipset registers, various hardware, all kinds of things like that, and enabling the various technologies that need additional configuration, like virtualization, encryption, various other exciting things that we paid for nice processors for. So the other half of that is we have platform functionality we need to talk to. And in the old days, that would be done by 16-bit real mode interrupts, and nobody likes that. That went out of fashion in the DOS days. So really what we're using today is something called ACPI, the Advanced Configuration and Platform Interface. And when you hear about ACPI, you'll really frequently hear the term ACPI tables. And this gives you a certain impression, a mental model of ACPI. Oh, it's a big bunch of data that you read, and it tells you all about standard components. There's PCI over here, there's power management over there. Wouldn't that be nice? In reality, you have a few of those tables. Mostly what you have is a pile of bytecode supplied by your BIOS and executed by the kernel in ring 0. Doesn't that make you feel so very confident? So BIOS itself has really gotten quite complicated for something called BASIC. It is based on thousands of pages of specifications. It's really quite ridiculous how much it has to deal with. It has a pile of hardware to put up with, including a lot of system-specific stuff on random laptops that wants to do something out of the ordinary. And it has to deal with new features all the time, new processors, new chipsets, all these other things. But at the same time, it's got a few decades worth of compatibility requirements to put up with. And when you break them, people are very unhappy. It has a very tiny bare metal programming environment where the prevailing wisdom is that C is a very high-level language. And it really doesn't have a large community of people looking at it. We have external observers looking at it and complaining and drinking heavily, but we don't really have much review of the code of a BIOS itself other than the people who wrote it. That's not a very good combination compared to the systems we have that are that have the same degree of complexity but have enough people to maybe get a handle on that complexity. So what can go wrong with this? Well, first of all, you could have these various CPU features that you've paid for that let you do virtualization, extra security features, encryption that just don't work because they haven't been properly configured or they've been intentionally disabled because some random setting in BIOS was set wrong. You could have your memory map that says your RAM's over here, your PCI is over there, and so on, incorrect. So you can't get your devices or most of your RAM, or your RAM is mapped on top of your devices, so you crash when you try to use it. Like, fun and exciting. You could get suboptimal power management where your system works, but you're using 1.5 watts more power than you really needed to be, and you're losing an hour of battery life that you could have had. You could have delays and latency, where there exists on x86 a mode called the system management mode that's specifically designed for the BIOS to take control on an interrupt, hide things from the OS, and then go back as if nothing happened. And this makes especially the real-time people really unhappy, especially when they say, oh, we can go off for 20, 30, 40 milliseconds and nobody will notice. Ow. And on top of all that, you've got all the other random things that can happen. You have USB handoff of input devices and that the BIOS needs access so you can use your lovely USB keyboard in the BIOS menu, but you need to access all that from the OS. That handoff gets done wrong rather often. You have BIOSes that think it's okay to, from SMI hidden from the OS, make use of one of the 2 performance counter resources available on the x86 to go read its own stuff, and make it so that the OS can't sensibly use it without disrupting the BIOS. There are only 2 of these. BIOS is stealing one, and some things can only be read from one or the other. Great. So all of these are rather severe bugs in BIOS that we'd really like to check. And on top of that, we might also want to explore a little bit and figure out what's up with all the other undocumented hardware on this board, like extra buttons, extra lights, extra switches, whatever you have on your laptop, server, whatever, that is some non-standard piece of hardware with a non-standard interface that you might still want to talk to from your very standard Linux system. So obviously, there's a lot that can go wrong. We'd like to run some tests on this so we can fix it when it goes wrong. So then the obvious question is, rather than doing this under GRUB, why didn't I test this under Linux? And the answer is that Linux is entirely too smart. In particular, Linux will take over from the BIOS whenever it can. Despite what I said earlier, it would like to take everything over from BIOS and ignore it. It just doesn't always know how to. It will update the platform and hardware configuration to whatever it wants whenever it can. It works around whatever bugs it can without, occasionally it'll report them in dmessage, but it will still work around them. And it really doesn't give you any direct access to BIOS interfaces without being the Linux kernel itself. Overall, the tests would have to share and play nice, and that's not a comfortable test environment for raw hardware and BIOS interfaces. Those interfaces don't share. So the ideal testing environment would be something that's comfortable enough that you have a nice environment, but at the same time, something that doesn't try to give you a whole operating system and ignores most of the platform features, just barely enough to get you a test running. So turns out GRUB 2 is really remarkably capable. It has 32-bit addressing. It actually gets out of real mode. It has most of its code written in C. It has novel things like malloc and printf that a lot of low-level environments don't. It can read files, though not write them. It has a basic menu system that lets you organize the various things you might want to run. But at the same time, it's a lot like DOS. It runs with a single thread of control. It doesn't go off and do things in parallel with a scheduler. There's no operating system to cooperate with. And it uses the bare minimum amount of BIOS interface that it can. It ignores almost everything else. So if it's broken, it probably won't notice unless you tell it to. So we started out with the idea of, I want to use this as a useful test environment. And the original goal was, let's get rid of all these DOS test programs that Intel had laying around to test all these individual facets of your system. And a new one gets written every time something needs to be tested. And in particular, we wanted to test the Intel power management reference code, this big blob of code that Intel hands to BIOS vendors and said, just jump to this with a little configuration and it will write out all of your tables for how your processor ought to do power management. And you don't have to worry about it. It will do it correctly. You would think with that, BIOSes would always get it right. Other than that, it also would be nice to poke at hardware in general. Go read CPU IDs, read PCI, have some environment where you can do low-level poking without getting in the way of the Linux kernel and making it very unhappy. So we added a pile of extra commands to GRUB that let you do this kind of thing on GRUB's command line. So at that point, we've got this replacement for a handful of tests, most of which are written in C. So we'd really like to replace a bunch of other one-off test programs and write a handful of new tests, but we don't really want to keep doing this in GRUB scripting language. As pointed out in the previous talk, we're getting kind of tired of cut-down scripting languages that we have to learn and deal with. And in particular, GRUB scripting is, their official name for it is Bashish. Take from that name what you will. And it's a subset of shell scripting, plus the bits needed to handle menus. It has all the syntax of shell, so all the magic meta characters you have to quote, even though most of them don't actually have the corresponding functionality that would be useful. Less than and greater than, you have to quote them, but there's no redirection. Great. There's no expressions, there's no calculation available. Anything you want to do that isn't just gluing pieces together has to be written in C anyway. And it's really just gluing pieces together into menus, which, in fairness, for what GRUB is intended for, that's just fine. But for what we were trying to use it for, it really didn't cut it. So in an effort to kind of provide a stopgap here, I figured, well, I maintained a static analysis tool for C for 3 years. I ought to be able to do this. Sparse famously has a comment at the top of its parser from Linus, stupid C parser version 1E-6. Let's see how hard this is. So I figured, all right, let's write a C expression evaluator. Take 64-bit integers out of the environment variables, run expressions on them, stuff them back in the environment. And how hard could that be? It turned out it wasn't that hard to write. What you get is something that looks a lot like this. So you have a pile of CPU ID calls here, pulling out information from the hardware, whatever you're calling, stuff it in the environment. So go get CPU ID function 1 off of CPU 0. Get the processor signature by masking off the low nibble, and compare that to this magic processor signature, and if so, you're running on a Nehalem processor. So it works, but shell is really not a systems programming language, and this is the most you're really going to want to do with it, and this is already pretty bad. If you're trying to write extensive tests of platform functionality that really looks like you're poking at things an OS would poke at, this is really not going to cut it. And the biggest problem with this is that nobody other than us would ever write any tests in this environment. That's a serious problem here because we want to build this framework, but if we're the only ones ever writing tests, it's not going to be a very large body of tests. So we wanted a real scripting language, and for us, the first thing that came to mind to deal with was Python. And in particular, the reason we picked Python was that it had a fair bit of adoption among people who, again, originally said C is a very high-level language, but there's a lot of other tools that are being provided for testing related pieces, dealing with Intel's equivalent of a JTAG, various other devices where you can script them with Python. So we figured, all right, let's provide a Python environment. So we ported CPython 2.7 to run inside the GRUB bootloader. So most of this involved writing a C and POSIX compatibility layer for functionality GRUB already had. In particular, GRUB had the ability to open and read files, but its functions for that were GRUB file open and GRUB file read, and it didn't have any concept of a position in the file. So dealing with that required writing a real open and read and fopen and fread, because Python uses both, that had that concept, that maintained those data structures and did all the bridging. And that's a pretty substantial layer, but still pretty much a compatibility layer. Other pieces, we had to write some floating point functionality because GRUB didn't have or need floating point support, but Python has a built-in float type and we wanted it to work. Maybe we want a percentage done in tests or several other things we actually use it for. It turns out there's a lovely implementation of libm available for under an all-permissive license called fdlibm, the freely distributable libm. So we grabbed that, dropped it into the project, and managed to support the various functions that GRUB needs. And then, well, Python is a language, but it wouldn't be much of a language without its extensive standard library. So we also ended up porting much of the Python standard library. We've got a pile more to go, but we want to port things as we know they work. So how do we know if something actually works here? We first of all needed to know, do we have all of the dependencies available? Well, Python has a lot of introspection available. We can go look at a module and say, parse this, tell me what all it depends on, and repeat that recursively, what you get is a graph that looks like this, courtesy of GraphViz. So this is everything we needed to run the regular expression module. Okay, that's not too bad, so we need to work our way up that stack, put all of those modules into the build, verify that they work in our environment and don't depend on some low-level functionality that isn't supported yet. And we did want to verify each one because since Python is a dynamic language, then we're not automatically going to know that because it compiles, because it doesn't compile. So we went off and tested all of these, made sure they worked. So that doesn't seem like that big a deal until now let's try the collections module, which provides various high-level collections. Yeah, that's a little harder. So the amusing thing is you can actually see a couple of major modules in this list despite it being ridiculous. This one right in here that's a big bottleneck with lots of inbound and outbound dependencies, that would be OS. And on this end we have sys. Those are pretty distinctive. The rest is most of a mess, but work through it and you can get all of these modules included, and we do in fact support collections and quite a bit of other standard library modules. And at some point I need to put the tool to generate these GraphViz graphs up on the BITS website because it's kind of handy. So apart from that, the other piece was dealing with C extension modules because we do need to interface Python with functionality available in C. So to deal with those modules, we couldn't just deal with them as Python does by building a shared library .so because GRUB doesn't have those. It does actually have something akin to kernel modules, and they are based on ELF, but they aren't extensible at runtime, unlike the Linux kernel where you can build out-of-tree modules and dynamic modules and whatever. You have to build everything at compile time, and you have to build those modules in a way that the GRUB build system understands. And it doesn't really fit with the way Python modules build. You'd have to wrap a lot of extra around each module. So rather than doing that, we ended up saying, well, we're shipping all this on a CD or a USB key anyway. You're not likely to take a running build of bits and throw more modules onto it. So let's just compile in all of the modules that ship with Python that we care about and build them into the GRUB binary, or rather the Python loadable module for the GRUB binary instead. And this works just fine. You add them to the table of built-ins, like things like sys. And the other piece we really wanted was we need all this access to Ring 0 platform functionality, so we added a new module, bits, that provides all of that access. All of the low-level GRUB functions we care about, all of the hardware functions, and then we can wrap that C extension module in various nice Pythonic interfaces to access it. So now that's great. We don't have to write much C. We write most of the stuff in Python. We can write all these tests in Python. So now that we have a real scripting language to work with, what kind of stuff might we want to talk to? Well, there's where those platform interfaces come in. We really want to talk to ACPI. And speaking, unfortunately, from experience, trying to hand parse ACPI in any way is a really bad idea. Don't do it. And after having learned that the hard way, we ended up looking at ACPI-CA, which is the ACPI component architecture reference implementation from Intel. It's a portable implementation of ACPI. It runs on most platforms out there. It's already what Linux uses and drops in new releases of every new kernel version. It has the bytecode parser for all of the pieces of ACPI that use code. It handles the various hard-coded tables. And it has an interpreter as well for running the bytecode methods. So we ported the Intel ACPI-CA interpreter and bytecode and all of the other pieces we cared about to run inside GRUB2 as another module, the ACPI module. And then obviously we don't want to access all of that from C, so wrote some bridges between ACPI and Python so that we could call ACPI methods from Python and get answers back. And among other things, this meant teaching Python all about the various types of things in ACPI so that we could convert back and forth. Apart from that, again, the less stuff we can write in C, the better, now that we've got a much more powerful high-level language. So we wanted all of those commands we added to GRUB before for exploration to work in Python. So based on that, we wrote an interface for bits to support commands registered to GRUB so that you can run them from the command line. But when you call them, the command line gets passed up to Python, which will do whatever it wants and return an exit code back to GRUB, almost like running a script. And at that point, you can use, for example, the standard Python argparse module and go parse command line arguments, generate output for --help. All of that kind of thing works very nicely. And since you can register arbitrary commands from Python, we also support running PyDoc from within GRUB, just so that you don't have to reboot to get documentation. It's kind of handy when you're stuck in a lab sticking a USB key into some big noisy server and you don't want to have to wander back and get your laptop. So apart from that, the less C the better, but also the less GRUB scripting the better. We ended up with a lot of things that looked like this. Well, we want to run this test, so let's turn on the pager, built-in equivalent of more, and let's run this test by going and grabbing it from whatever Python module it's in, and then turn the pager back off so that we don't get press enter to continue halfway through the GRUB menu. And repeat this for the umpteen tests we were adding. So every time you write a pile of Python code, you had to write this little bit of GRUB scripting as well, and that's kind of ugly. We don't really want to be writing anything other than Python if we can help it. This is obviously generatable from Python. It's pretty trivial. You go look at a list of tests and generate it. But the problem is GRUB expects to read this from a configuration file on disk. And it has no ability to write files, so we couldn't just run a Python script and write the output to a file to read the menu. So given that, we implemented a fuse file system for Python. My, that's a well-shaven yak. So GRUB already has devices like HD01, CD, whatever things that it needs. It has a hardware device to access raw blocks and file system drivers to access the files on that block device, depending on what file system it has. We wrote a device Python, in parentheses, that whenever you access it, read files out of it, or try to ls and look at all the files in it, it will go call Python callbacks to figure out what is in this file system. And based on that, you could then register files to be called from Python. Here's my open function. Here's my read function. It's a lot simpler API than Fuse, obviously, since we don't need to support things like mmap and ioctl and other craziness. But it works. And it lets us do crazy things like source python/test.cfg. Now we've got dynamic menus. Also do logging via this. And now we can add a brand new test by writing a pile of Python, registering the test in Python, and rebuilding and shipping. No C, no GRUB scripting, just a new test. So the last bit here is, again, we have no writable file systems, but we're running a big pile of test suite. So if something goes wrong, you'd really kind of like to know what went wrong. So we have logging available. We capture all the output that Python generates by hooking into sysstandard_out and sysstandard_error and duplicate it to an in-memory buffer. And that buffer is then made available again via that same Fuse file system. So we can go give you a menu entry that just does cat that inside a pager and let you review the log. And if you want to capture it for later use and don't want to pull out a digital camera like you usually do for a kernel panic, then instead you can save it to an ACPI table because, hey, we have a convenient function to write ACPI tables out. So we create a magic ACPI table with 4cc bits, stuff our raw data into it, and from inside an OS like Linux, you can pull the table right out of sys firmware ACPI tables, skip the ACPI header, and you have a pile of plain text log. It works. So apart from that, let's look at the basic set of features that we have at this point. We've got SMP support in GRUB. You can go call other processors from within GRUB, run arbitrary C code, and use callbacks to run other kinds of code, and then come back and take all of that data and do something useful for it. So, read a CPU ID on CPU number 3. You've got Python scripting available in a Ring 0 environment. That's a really fun area to play in. You've got Python modules for all these different platform interfaces, including the CPU-specific bits for all these different new CPUs, anything Nehalem and newer, because we haven't been digging back into old stuff that isn't really sold anymore. And if somebody wants to look into doing Atom support, that would be awesome. We haven't looked into it much. PCI, PCI Express, poke devices, figure out what they're configured as. ACPI, including doing the decoding of the tables, the bytecode, running methods, getting the data back to Python, doing logging, and handling this whole test infrastructure. 27 of 28 tests passed. So given all that, then we can support the test suite that we started out trying to write. So some of the tests that we actually have available in bits, check your power management configuration. Figure out if you're most optimally configured to save as much power as possible, including your ACPI tables and your various processor registers. Figure out if you're getting maximum performance. Again, there are all those tweakables available in the CPU. Did the BIOS set them correctly? Figure out your frequency states. Go walk through all the available processor frequency states and check that you're actually getting that frequency. Figure out how much you get when you're getting turbo available. Figure out how well your processor sleeps, and when it does sleep, how long does it take to wake up from those deeper sleep states? It'll take longer. How much longer? We can check the various configuration registers of the CPU. We have a histogram for how long SMIs take. We can say, hey look, you're getting about a 10 millisecond SMI every 250 milliseconds. And that makes it a lot easier for BIOS vendors to say, oh, that's the quarter second SMI to do, and exactly. Now you can get rid of that by tracking it down and know, okay, that was what our problem was. And when you look under Linux and you're saying, well, we're getting these weird problems every n seconds, you can track down which one it is. And we can also test the USB handoff mechanism as well. So you can hand off from the BIOS to the OS, figure out how does that affect your SMI, how does that affect your ability to go to sleep. Turns out both of those things are often broken while the BIOS has control of USB. Unfortunately, that's a test that you tend to run and then reboot, because once you've handed the USB control from the BIOS to the OS, and GRUB doesn't really know how to talk USB, or rather it does, but it can't both do that and talk to BIOS, then you don't really have the ability to interact with GRUB anymore. Plus, if you booted off a USB key, that's kind of painful. And technically, it's possible to hand the control back from the OS to the BIOS exactly the same way. No OS does this, so guess whether it works or not. Or perhaps I should say Windows doesn't do this, so guess whether it works or not. So the other really awesome thing about working with this test suite is it's not just something we run and complain to BIOS vendors about. We actually have BIOS vendors looking at this and running it before they ship their boards and their BIOSes. This is a really amazing thing. They actually fix bugs in BIOSes. It turns out that BIOSes kind of have two development modes. We only tend to see BIOSes in the mode where they've shipped a BIOS, and therefore they've shipped version 1.0. They're only ever going to release point releases for critical bugs that break horribly. They're not going to want to make any changes where the risk of breaking something with that 20 years of backward compatibility is greater than just saying, okay, it's a little suboptimal, we'll live with it. But when a BIOS is being developed, on the other hand, sure, yeah, that's broken, let's fix it. It's like reporting a bug to a regular free software project. You may not get to see the code, but they'll fix it in a vaguely timely fashion. So at that point, we've got all of the functionality of bits, we've got all the tests of bits, so at this point I want to give a bit of a demo. So let me see if I can pull this up. No, I'm going to invert the colors in just a second as soon as Why did that not come to the front? Sorry. I have a window right there where my cursor is. Awesome. That should be more readable. So what we have is we want to test the ability to do an ACPI method call. So let's take a look. Yes, that would be a very good idea. Is that readable? This is ACPI code. This is what the source form of ACPI looks like. So we've got a couple of methods here that are set up to be in an SSDT, an supplementary system descriptor table, which is one of the various tables that loads when you boot up your system. And it has various scopes. So at this point we're saying at the top level scope, create a couple methods. One with the signature of add_to, which will take its 2 arguments and it will add them and return the result. We have a cat_to, which will take its 2 arguments, concatenate them as strings and return the result. So ridiculously simple methods, but they provide an example of taking arguments and doing something with them and returning a result. So given that, we can compile that table. Not expecting it to be quite as sharp an angle to be able to look at the screen here. So running the Intel ACPI compiler, compile the source code to a binary ACPI table. You can look at that and see it's a pile of binary, but it has the various codes in it you would expect to be able to read. So at this point, we can run KVM and tell it, turns out KVM can load ACPI tables from a file and add them to its BIOS. So please load this ACPI table from a file, boot up this CD. And this, unfortunately, I don't think I can change the colors on. So if anybody can't read that, then maybe we should kill the lights for a moment. Unfortunately, I can't, as far as I know. Can I? Hey, that's awesome. Thank you. That would have been good to know. Okay, so this is the top-level menu of bits. Gives you access to all the interesting functionality. We've got a pile of tests available. We've got the ability to look at the logs, play around with various other things. This is our auto-generated test menu. It's not very interesting on KVM because we don't have that many tests that run on KVM. Working on fixing that right now, actually, with some patches to let you have KVM pretend to be a better processor than it actually is and simulate various pieces. But we can also go back to the command line here. You can run any kind of Python code you want, obviously. So let's go ahead and run some ACPI. We can evaluate an ACPI method. So we want to evaluate the add_to method. We're going to pass it. Is that getting? Great. Hang on. There. Not getting truncated now. So yeah, we can add numbers by the most convoluted means possible. But we can, more importantly, we can take an ACPI method, look it up in the tables, verify that it exists, parse the bytecode, figure out how to execute that, convert Python integers into ACPI integers, pass them off to ACPI, interpret the bytecode, get the answer back, convert it from an ACPI integer back to a Python integer, and return it to Python. And then add 2 numbers in the most convoluted way possible. So similarly, we can handle whatever types were thrown at from Python, because hey, you can introspect types in Python. So you can concatenate strings in almost the most convoluted way possible. And either way, we're taking the appropriate type and dealing with it. So you can also concatenate other types of objects, like a buffer. We have types corresponding to the various ACPI types. So you could have an ACPI buffer object of, hang on. That would be, and it concatenates it in hex. So what we've actually got here is a 2-byte buffer for ACPI of raw binary data. It's being passed to ACPI as a binary buffer. And then the concatenate method in ACPI is taking that and saying, oh, well, I know how to do that. I turn it into a hex string and concatenate it. And it ends up giving me back a result as a string. This is important because quite a lot of methods in ACPI take big, ugly binary data structures, and we want to be able to deal with those. Python has mechanisms like struct.pack that let you create strings containing raw binary data. This is what lets you pass them off to ACPI as the appropriate type and deal with them. And I think that's all I'm going to be doing with the demo screen there, so if you could hit the lights again. Thanks. Awesome. So yeah, same thing you just saw, just in case the demo didn't work. So the other thing I want to go through, and not going to go through that again, I'll just show you this version, is how do you write a test for bits? You have something you want to test. Say you've put this add2 method into a real BIOS for some crazy reason, and it's become if not wildly popular, then used by some popular OS, and therefore we can never get rid of it again. So therefore we want to make sure it works correctly and actually does add 2 numbers. So let's write a test for add2. So here's the patch you need to add a new test for ACPI methods to bits. You add the 3-line method here for adding a couple of tests. We first verify that the world is still sane, so let's add 2 plus 2 and make sure the result is 4. Great. Then go evaluate the ACPI method for adding 2 plus 2 and print out a test result here for what result did we get from add 2 of 2 plus 2 and what result were we expecting. So the net result you get from this is you have an ACPI add 2 menu entry added to the ACPI tables menu under the test menu. And when you run it, first of all, if you run it without the add2 table at all, you'll get a test failure. So you get something like this. Hey, I ran this test, it failed. So 1 test passed, 1 test failed. Well, yes, 2 plus 2 is still 4, but this test didn't work because we got back none. There was no such method. So basic test suite, throw in the ACPI table, all of a sudden the test passed. Basic stuff, but if you take that and apply it to a real system with all the tests we have available, you get something more like this. And this is actually a real BIOS on a real system using the latest generation Intel processor. You've got a 64-way system here with a whole pile of brokenness. It doesn't have a correctly written table for the APICs on the system. It doesn't know what IDs the processors have, so it's warning about that up at the top. Some of the other tests passed. And we have kind of a catch-all that says, go look at all the model-specific registers on all the processors, and except for a few cases where we know they're supposed to be different, in general, if they're different, it means the BIOS screwed up somewhere and said, oh, I programmed this on the processor I booted on, but didn't go do it everywhere else. Turned out in this case that it completely failed to program MSR 42B, which I've utterly forgotten what that one is, but one of the useful MSRs for programming the platform configuration. And you want it to have the same value on all CPUs. In this case, it has 4 different values on 4 different sets of CPUs. Specifically, these are the 16 different CPUs in each of 4 sockets on a system. Each set of 16 CPUs had 1 value, and they all should have had the same value. So it's nicely summarizing here which unique values you got, which CPUs you saw them on, so you can figure that out and fix it. So we've got a real test suite. We've got all the infrastructure to support a real test suite. At this point, the big thing is we could really use a little bit of help. We have 2 developers working on this project, and it'd be awesome if you have any kind of platform functionality you care about, if you work on virtualization, if you work on real-time, if you work on something where the functioning of the BIOS or the ACPI tables or any other part of low-level hardware configuration matters to the functioning of your software, and you've seen bugs on this in real systems, tell us what they are and we'll help you write tests for them, or we'll show you how you can write the tests for them. And again, the nice thing about this is we actually have people looking at this on new BIOSes before they ship. So if you get a new test written and added to bits, we will help make sure that new BIOSes do not get this wrong. You have a regression test suite for BIOSes. Add things to it. So that's all the information I have on bits. You can grab an ISO image of bits and play around with it, boot it in an emulator or boot it up on a real piece of hardware. If you want to hack on it, you're probably going to want to download the actual source code, be able to add to it, build an image yourself. You get to play with low-level functionality in a high-level language, and drop us an email if you have any questions. And speaking of questions, do you have any?
I was wondering, after you're doing your ACPI checks inside GRUB, how do you validate that against a booted Linux kernel, since presumably they have quirks files in the kernel and a lot of other things that are going to mangle it before you get to it?
So the question was, once we've validated all of the ACPI tables from GRUB, how do we validate in Linux that they're being handled correctly, given that Linux may have quirk tables that overrides whatever the BIOS might do? Our goal is to test that the BIOS is doing things correctly, even if Linux might know how to work around a particular bug. So obviously, our highest priority are things that Linux doesn't know how to work around. Those are the things we're going to want to add tests for first. But we do want to verify that the BIOS is actually following the whole spec for the benefit of any random version of Linux or any other OS that might be running. So we're not really trying to test the quirked ACPI tables that Linux may be overriding things with. We're just testing what the BIOS ships. Does that answer your question? Okay.
Hi, Josh. CPUs often have power management features which the BIOS won't tell the operating system about. You said that Intel would give BIOS developer a table or a program which will generate tables for a particular CPU. Is that included in bits? Like, will I be able to run bits and say, okay, my CPU supports these features, but the BIOS is only reporting these?
I see. So the question was that you have all of this power management code, or for that matter, other kinds of code that's being run in the BIOS to generate data made available to Linux, like the tables for processor frequency and sleep states. And if your BIOS is doing this wrong, is there some way Linux can then do it right and override the BIOS? Is that?
Well, I know that Linux can override it, but is there a way for bits to
help with that?
To help BIOS
So there's a
developers?
couple answers to that. One is that as part of working on this project, we've also been working on getting more and more of that early BIOS level documentation and reference code made generally available. So one of the things that we've managed to do is get the power management reference code, the bits that actually generate, based on your processor, all of the P state and C state tables, made available as open source under the MIT license. So hey, if the core boot people want to drop that in, or if you want to adapt it to work in Linux, that would be great. And so that's half of that. You can take that code and use it in whatever system you're working on. Bits also has that ability. I was primarily talking about testing here, but we also have the ability to change the configuration of your system and override it to have the proper configuration. And given that we're running in a bootloader, oddly, we can then boot an OS. So if you want to run all of the reference code to reconfigure power management, and then from that point go boot an OS and have it be correct, you can in fact do that. The one caveat I'll supply there is that there's various features of the processor and other pieces that can be locked by the BIOS to prevent changing later. Obviously, there's nothing we can do about those, but anytime that isn't the case, we can change your configuration, update it, and fix it. Anytime that is the case, we can at least tell you it's wrong and let you complain to your BIOS vendor so they fix it, and try to make sure new BIOSes don't have that problem.
Cool.
I think there was a question up here. Okay.
Is there any reason to keep the GRUB shell now you've got Python? I mean, you can use Python in interactive mode.
So the question is there any reason to keep the GRUB shell when we have Python and a Python interactive interpreter? The long-term answer is not really. We do want to have the GRUB shell available because there's other things you might want to do, like go boot an OS that you don't have a menu entry for. But we would like to directly make the Python REPL available so you can just type at it without typing py and quoting your string. The main difficulty there is we need to implement proper support for sys.standardin, which GRUB doesn't provide us very much infrastructure to support. As soon as we have that working, and we have it almost working at this point, you can do single character input, that kind of thing. As soon as we have that working, we can get Python readline working, and we can get the entire interactive interpreter working, and yes, we desperately want that.
Is it possible to just install, I got GRUB on this laptop, would I be able to install bits on this, or would I need to sort of reorganize my partitions to allow it to fit?
So the question was, you have a laptop, it already runs GRUB, could you install the version of GRUB that comes with bits onto your system and use that as your standard version of GRUB? Yes, you could do that, and you could install that version of GRUB and put the necessary files in the location where it expects. I wouldn't really recommend doing that at this point because it's more designed to run from a separate USB key or a bootable CD. It certainly works. We would want to, among other things, update to a newer version of GRUB at some point in order to handle that. At the moment, we branched right before the point where they rewrote their entire build system from custom Magic Ruby stuff to Auto Tools. And sadly, Auto Tools is in fact better there. But, low bar. But at the same time, we haven't yet gotten all of the pieces we needed forward ported to current versions of everything. Apart from that, we haven't really added any interesting functionality to the bootloader aspect of GRUB. It's still just a bootloader. So given that, I think you'd have just as much success booting it off of some other media and running it from there, and you wouldn't really gain anything having it on your hard drive. That said, there is absolutely nothing preventing you from doing that. It works just fine, and we've done it on systems that had no USB and no CD. We imaged it to a hard drive and used it from there. And you would not need to reconfigure any part of your setup, partitions, whatever. You would just need the standard setup with /boot. And in /boot, in addition to containing all of the GRUB modules, also contains all of the various modules for Python, all of the configuration files we've added. So it's pretty self-contained. Does that answer your question?
So in other words, it doesn't need a lot of code right at the beginning of the hard disk?
That's right, yeah. We haven't changed any of the bits that bootstrap GRUB off of an MBR. We haven't changed the bits that make GRUB a bootloader. We've added some new modules that give you Python and give you ACPI and give you all this other functionality, but those are just loadable modules that ship in boot GRUB. And you, unfortunately, I mentioned earlier that Bits has loadable modules, but they don't work out of tree. You can't, unfortunately, take the various modules we've added to GRUB and directly drop them into an existing GRUB install. You would have to use the version of GRUB and the modules of GRUB we've built. Other than that, it will work just fine. Nothing special going on there.
Just one last thing. EFI, is it possible to have this work in any way with EFI?
We have successfully booted it from EFI using the legacy BIOS compatibility, CSM compatibility services module. If you want to boot it natively via EFI, you'd have to use GRUB EFI. There is that support. We have not yet ported this to build with GRUB EFI. The main annoyance is you can't build it both ways simultaneously. You have to build GRUB either for legacy BIOS or for EFI. And you can't have both in the same image. So that's build system annoyance and complexity, and we don't really want to ship 2 entire ISO images, but we may end up having to. Any other questions?
Yeah. I was just wondering if you could have perhaps, did you think of using UC Linux instead of GRUB to, as a base? Wouldn't that be any good?
So question was, could we use UC Linux instead of GRUB? Using UC Linux as opposed to regular Linux doesn't really help us in any way. It's smaller, it relies on less hardware, but it still has some decent expectations of what the system does, and it's going to load a pile of drivers. It's going to need to access pieces of the disk, it's going to need to access pieces of this, that, or the other. It's going to change configuration, it's going to execute a pile of ACPI, it's going to switch from BIOS mode to OS mode in ACPI. It does a pile of things that an OS is completely supposed to do, but which make it very hard for us to test BIOS. We really desperately needed a pre-OS environment to look at the state of the system before a real OS takes over and runs. We did seriously consider, can we make this work in Linux? The answer was it really didn't seem very feasible. This seemed so much more straightforward. Question up there, I think.
So I guess the devil's advocate question is, if platform OEM vendors are going to eventually move to EFI, why not do it for EFI in the first place?
So the question was, if everybody's moving over to EFI, why not do this via EFI in the first place? I'm assuming you mean, in terms of the previous question, are we not using GRUB EFI as opposed to GRUB Legacy? There's a couple answers, sorry, not GRUB Legacy, GRUB's support for booting from BIOS. There's a couple answers to that question. First of all, there's a huge number of systems out there that boot as a BIOS and not via EFI. In addition to that, all of the systems currently available that use EFI, with a few exceptions, boot using the legacy boot module instead of or in addition to booting natively via EFI. So if we write it for BIOS, we get all of them. If we write it for EFI, we can't test any system that doesn't boot via EFI. So we would definitely like to support both, but if we're only going to support one to start with, it makes sense to do the one that has a superset of all of the available systems as opposed to just the subset that does EFI.
Fair enough, fair enough.
Okay. Any other questions? I think I saw a hand over this side of the room. No? Okay. All right.
In which case, let's thank our presenter with a round of applause and this gift from Linux Australia. Thank you.
Thank you.
That's our final talk for